So I do actually have an awful lot of stuff to go over, and people are going to be welcome to wander in at any given point in time. I am going to encourage a lot of questions and participation, but I also am going to go through these slides very, very quickly. We're not going to be staying on anything for an extended period of time. So feel free to raise your hand and just go, hey, yo, asshole with the hat, take my question. So basically, I'm making a plea for everybody, for consumers, for vendors, for developers, for architects, for something I'm calling floor awareness. And by floor awareness, what I'm referring to is in dancing, when you do dancing and you are the lead in a dance, your responsibility is to make sure that your follow doesn't get hurt. It's your responsibility. And in order to do that, you have to have floor awareness. And that floor awareness means you know what's going on around you. You not just know the space that you occupy, but also the space that other people who are dancing occupy, how they're moving, how they're fitting in, and how their dancing styles can actually affect you, even though you're not dancing with them. So floor awareness is a general understanding of what's going on around you. I'm going to apply that to storage, because as we've been going through some of the things here inside of the SDC, we've been seeing everything from SMB to NVMe to Fibre Channel to Rocky to iWarp. We've been talking about all different kinds of things. Many of them seem independent, but in reality, everything is related to everything else. So we're going to be talking about a different way of thinking about the perspective of storage and examining something that I'm calling vertical storage. It's not an industry term. It's not a standard by any stretch of the imagination. It's a different way of thinking about storage. And so far, when I've been introducing this in general ad hoc conversations, it seems to be resonating. And so I wanted to try to flesh it out in a more formal manner. And then I'm going to be able to provide exactly what this all means in context. So let's start talking about what I mean by the horizontal versus the vertical. Any storage system has a constant pressure, and this includes storage networks, and includes storage devices, includes storage philosophies. And they really come into a triumvirate of evil, which is you have these pressures, these magnetic pulls on you and on the storage systems themselves from one side or the other, and they basically work in opposite directions. And one of those directions is performance, and that's when we start talking about things like NVMe. And we start talking about 3D Crosspoint and ZNAND and a lot of all these other so-called storage class memories. In other words, anything under 10 microsecond latency. Right? Really high performance storage systems that also act as memory are something that are keeping a lot of people up at night. You've heard about the conversations about key value, which is going to have, there's another presentation coming on later in these sessions. And it's all about how we can actually create the systems which can take advantage of these. This is contrasted with the scale problem. In other words, scale and performance are often completely diametrically opposite. Right? We build systems so they can work with these trade-offs. In order to increase your scale, you're going to necessarily lose your performance unless you want to do this in a very fine-tuned manner. That means you lose your manageability. So this is sort of like fast, cheap, and quick. You only get 2 out of the 3. Well, you get 2 out of the 3 here. And you have to try to find that sweet spot. Then you work on the storage network, which overlays on top of this, and it has its own set of storage forces that it has to manage with. So what we're going to be doing is we're going to be taking a quick look at what these things actually mean. And normally when we start talking about these things, we all look at this particular kind of address. We look at it from a horizontal perspective. That is the connectivity between different devices. Every single system inside of a data center has 3 basic components. You've got a compute component, you've got a networking component, otherwise known as an interconnect, and you've got a storage component. They all start looking like this. And it focuses on the connectivity and how these things work. You start talking about the parts, naming of the parts, naming of the pieces of the parts. Let me tell you what I'm talking about. When we start talking about why you want to use different technologies, what does it look like? Well, if we're talking about Fibre Channel, you've got a Fibre Channel HBA connected into a Fibre Channel switch, and you've got Fibre Channel storage, and then you put together your numbers on your IOPS and your latency, and poof, you've got your hero numbers. Okay, let's see if I want to do this with, I don't know, iSCSI. Oh, crap, it looks exactly the same. So I got a host, and I've got a network, and I've got storage. Well, what if I want to do with NVMe over Fabrics? Looks exactly the same. I've got a host, I've got a network, and I've got a storage target. I got my IOPS, and I got my latency, and I got my hero numbers. Oh, what do you know? NFS looks exactly the freaking same. But what do we do with those hero numbers? We create charts. We love charts. Charts that go up and to the right. That's what charts are supposed to do. And so our hero numbers make great charts. And that's how you actually determine whether or not you want to buy Fibre Channel, or you want to buy NVMe or Fabrics, or you want to buy iSCSI, because that's how you know you can get better IOPS and better performance with your NVMe appliance at the top of rack, because now we've got 96 million IOPS in one RU, and aren't you glad, and just buy my stuff? Why not? The problem here is that we take the advantages of the horizontal view, which effectively explains the relationships between the parts. And whenever you're learning a new system, it always helps to know what the names of things are. And we break it down into the different components, and we try to zoom in on these different elements. The disadvantages here and the problems that we have is that it doesn't really give you the big picture of what you're looking for. You start off in the middle. It begets the question of why you want to do something. Remember those storage forces that we were talking about? Are you talking about affecting the performance? Are you talking about impacting your scale? Are you talking about impacting your manageability? All of these questions are presupposed when we start looking at a horizontal view of storage. So people will tend to connect the dots, literally, by understanding how they understand the different meanings. So if you don't know what an HCA is, or if you don't know what an HBA is, you may assume that a NIC is better, not knowing that the functionality actually winds up being the same. One of the things that we've been doing at SNIA is trying to create a series of webinars for people who are not storage geeks. In other words, they're intelligent people, but they're not versed in the terminology of storage. Developers, programmers, virtualization guys, network guys, they all have to interact with storage at some point in time, and they at least should know the vocabulary. So we're creating a series called Everything You Want to Know About Storage, but We're Too Proud to Ask. Because what we're trying to do is avoid the religious conversations of one type of protocol versus another. And yet, what are the conversations that I've been hearing and seeing inside these things? Well, Ceph is better than Gluster, and NVMe is better than SCSI. And the thing is that they all have specific use cases and sweet spots. So when we have to ask these questions, we have to understand what are the trade-offs that are implicit in these, as opposed to trying to figure out how to shoehorn a particular type of solution in. For example, I have to have a very fast access for my data application. What should I choose? Shall I choose a hyper-converged system? Shall I use the top of rack? Shall I use rack scale? Shall I use a traditional storage array? What should I do? I have another problem. I need to have a multiple users, share a single storage device so we can have their home directories in a centralized location. That is not the same problem as the first question, nor is the third one. I need to store a lot of images all over the world. So if I'm going to be talking to somebody who's got a HyperFlex, and that's a Cisco product for hyperconversions, by the way. If I've got a HyperFlex customer, and I'm beating up myself here so that you don't have to worry about I'm beating up on some other competitor, okay? But if I've got a HyperFlex hammer, then all of a sudden my global images all over the world is a really bad nail to try to hit. All right? So we're not going to, as they say up in Maine, you can't get there from here. So what I'm asking is that we look in a much more vertical approach. So I think I hit this twice. So we take the horizontal approach and we effectively try to expand it a bit. Now the question is, what does this actually mean? So let's examine the vertical. There are many ways to solve a problem, and a lot of times you actually get some overlap in the type of solutions you can get for a particular type of problem. You can easily get very confused as to which ones to choose, especially if you have a bias towards what you already know. Now, as we start to move into new technologies such as NVMe, for example, the overlap actually extends far beyond just the protocol. Because what we're doing is we're fixing a major shift inside of our mental paradigms for what problems we're trying to solve. Right? SCSI and NVMe are two similar functional programs. They do something very different. But NVMe does something that nobody I've heard actually talks about. It affects the concept of time. Time in NVMe is actually the greatest asset that it has. But I haven't really heard that focused on in a lot of the conversations. We talk about latency, and that implies time. But as we start to look through the different use cases for these things and the different approaches that we take, the question you have to ask is, what does the concept of time mean when it comes to these different alternatives and the different resources we have to apply them? So the big problem we have to be careful about is that as these overlaps start to spread from one side of the equation to the other, you get these danger zones. And these danger zones can be really, really bad. And like data loss bad, like in people dying bad. Because if you apply the wrong connectivity options for the wrong use case, you can have very unpleasant results. So you have to be careful of these danger zones, and we're going to go through them. Now, I'm not going to go through the basics. I did have it in the deck, but obviously you guys know what this is, and I want to make sure we all level set. But I think this is a pretty decent level set where we are. So let's take block storage, for example. Block storage is what we consider to be a hot storage. It's very close together with the host. It's very latency sensitive. You can have an ownership, a one-to-one relationship between the host and the storage target, and that is a fundamental paradigm that we use for block storage. It's very low level. It's designed specifically for high transactions, rapidly changing data. And when we start to think about moving outside of a data center, then we have to become kind of careful about it. All right, so let's say inside of the host, a PCIe NVMe. Now, when I say NVMe, I'm referring to the PCIe form of NVMe, not the fabrics version. I'll be very specific about transports and fabrics versus regular NVMe. So when I say NVMe, I mean PCIe. So PCIe is co-located, the host and the storage are in the same place. It's a memory-mapped architecture. The memory of the storage is acting as the registers for the CPU itself. The communication goes naturally between the CPU and the storage using the PCIe bus. Moving outside of a server, however, becomes something of an issue because PCIe as a protocol is not designed specifically to be a fabric, which means that if you put a bus on an extended metaphor, you can wind up with a lot more problems because it just wasn't designed for scale. Again, the storage forces that we're talking about, performance and scale. When you try to move beyond the comfort zone or that sweet spot, you can get into trouble. Distance outside of a data center using PCIe is just simply a non-starter. You can't do it. So inside of the data center, what do we do when we want to move outside of a server? Now, you can use a PCIe external switch, but then you have all the problems with PCIe that you can make up for inside of a server. But outside of the server, we have other means of basically connecting our host to our targets. Fibre Channel, FCOE, iSCSI, Rocky, these are all good layer 2 block protocols. But, I'm sorry, iSCSI obviously is not layer 2. But the block protocols that have a very specific functionality inside of a network. In other words, you do not design block storage as if it was an object store. Bad things can happen, right? Because you have to be careful about the distance considerations. You have to have a very rigid architectures that you apply because all of the protection for that data has to exist inside of the network. You can't rely on upper layer protocols to fix problems most of the time, especially on the lower level stuff. Now, obviously with iSCSI or iSER, you're building in some of that protection as well, but you still have the fundamental rules of block storage of the relationship between the host and the storage target. All right, what about file systems? Well, when we start talking about the file systems, we're really not talking at all about inside the host. We're talking about what's going on inside of a data center, but you can also do some interesting things over distance as well. File-based protocols are often used for disaster recovery, but you can do low-level remote kinds of directory mounting. When I worked at Apple, we used to do this all the time. We would mount remote directories over long distances, as long as it wasn't often accessed. Right? It was just basically sort of sitting there as a, kind of a basic repository. The Dropbox system, for example, is an example of a remote file system based protocol. It's designed specifically for sharing among clients at scale because you don't have a one-to-one relationship, and that becomes a particularly keen thing if you need to do sharing data. So obviously, your distance can be distance will be normal for whether you're inside of a data center or outside of a data center, but your use cases are going to be sensitive to that time element. Object storage, in particular, is useful for really long distances. Right? You don't need to have the one-to-one relationship at all, simply because of the fact that there really isn't a relationship. You're asking for a particular object, or you're giving a particular object in a different location, and it can be anywhere. Again, we're not talking about performance here. Performance is not designed specifically for something like object, and that is actually one of the big problems that object stores have been having lately, is that they're trying to mix and match their use cases to force fit the tool that they have in the toolbox. Nevertheless, object storage being the least performant means that it's really good for things that don't change at all. all right, or changed very, very rarely. It's designed for scale from a distance as a thing. So what happens if we start looking at these things in terms of scope? So as we start from the inside the host and we move outside the host, these all have different kinds of applicability. So inside the host from PCIe, this is from a networking perspective. You move inside the data center, you got your Fibre Channel, you got your Ethernet, you got your FCOE, your iSCSI, your Rocky, you got your iWarp, and even some NVMe-OF. And you got your InfiniBand, although not a lot of people are using it. And then when you're talking about your major distance, you're really talking about Ethernet, right? Okay, what does that mean in terms of form factor? Inside of the host, you've got an NVMe, you can have an appliance, you can have a rack scale or top of rack, and the interconnect with PCIe can make sense in certain cases for turnkey solutions can be done with PCIe. If you want to have something with a little bit more scale and robustness, you can use traditional arrays. You can do software-defined storage. You can even have hyperconvergence or appliances at top of rack. And if you want to do distances, you've got your disaster recovery and archiving capabilities. You've got your effective cloud data stores. And in the future, if you listen to what's going on here at the conference, everything's going to be key value anyway. So, let's put it all together for us, just for the sake of argument. So before I get started, because now we're going to start getting into the intricacies of some of the protocols. Any questions or comments so far that you want to pipe up and you want to tell me I'm completely out to lunch so far? So far, hopefully this isn't really earth-shattering. This is a lot of prep. Okay, cool. This is the post-lunch coma. Is that what this is? All right. Well, only 2 people are doing email, so that's a good sign. So with this particular case, when we start to think about vertically, and now we're going to be mapping where these protocols actually fit, trying to understand exactly what we're trying to accomplish with this particular metaphor. Like I said, this is not an industry standard thing, and quite frankly, your mileage will vary. Not everything here is a rigid delineation. So keep in mind that these are kind of fuzzy blocks. They're not really. They're not rigid things. So if we start from the inside of the server to the outside of the cloud, from the top down, what do we have? Well, these are basically the kind of characteristics that we're looking for these classes of storage, right? So inside of the storage, we have buffering and caching, we have load store operations, we have local I/O operations. In the conversations that I've been hearing here at SDC this year, what this means is that a lot of the confusion we've been having about which ones to use, using that horizontal approach, are really playing around in the buffering and caching load store versus I/O operations for using really fast memory as capacity storage outside of the server. It's amazing how this one particular graph maps onto the conversations and the questions that I've been having in other sessions. What about the local network? The local network is where we start talking about the things like NVMe over fabrics and whether or not Fibre Channel or iSCSI or ICER or Rocky or iWarp or all these different things, or NVMe over TCP. All these different things are going to be playing in that kind of space. And most of the conversations that we have are going to be focused on that if we're talking about enterprise data centers. The big difference, however, is that as we start to look at the internal storage up here, it's bleeding into the green and the other way around. That's why we're looking at this from a vertical perspective, is because when we start asking questions up here and we're really meaning down here or vice versa, we can get lost and get in trouble. All right, so the next thing we're going to be looking at is, the external wide area network. Now, for a long time, this was the purview of disaster recovery and business continuity, and there were very different things you had to do to plan your networks. The propeller spins the other way when it comes to distance, especially if you're talking about block. But what happens is now we're talking about the external wide area network technologies that apply into the local data center. So why wouldn't you do the wide area network inside the data center and just get the best of both worlds? Well, we'll talk about that in a second. Excuse me, I feel like I'm 14 years old. Today we're going to talk about. And then we start looking at, as we start to expand our scope even further, when we're looking at the global network and the cloud, basically what we're looking at that point in time are really massive scalable systems, and we've completely given up the ghost when it comes to performance. So at that point in time, the trade-offs as we've been moving is highly performant, highly scalable, and where the management circle, which is not here, has to be placed. Because that's where the big danger zone winds up being. And now as we start to apply this into different types of protocols, you can see in particular where people are getting in trouble. So this is what I call the vertical map. And like I said, your mileage is going to vary. It's not rigid, and so bear with me. But this is a guide to help us understand where the technologies are really going to play. And because of that, we can actually look at the approaches that we're trying to take and where the sweet spots of these different technologies are trying to fit in. You'll notice that many of the different technologies fit into multiple layers. You will notice, for instance, that we've got iSCSI, NFS, and SMB in the external wide area network at the same time as in the local network. What happens then, though, is we have danger zones. So the sweet spot of one technology can fit, technically, inside of another layer, but the problem winds up being that you have now reached outside of your sweet spot and are entering into the danger zone. Just like when we extend PCIe outside of its server, we are entering into a danger zone because it's not technically a fabric. It will work, but it doesn't have a lot of the high availability and recovery mechanisms that we expect inside of a network outside of a server. So when we start to look at these particular things, we have to understand what the trade-offs are. We have to understand where the risks are going to be. So as developers, I'm asking you to think about where these things are fitting on a vertical scale, not just from a connectivity scale. And now we're going to be starting to bring these things home, and so that it's hopefully going to be starting to make a little bit more sense as we go through some of these examples. So let's take a look at some of the characteristics of local storage. Inside of a server, we're talking about what's happening inside of the bus-based architectures. We're talking about the need for storage to be applicable as a memory device and or a storage device, and what that means in terms of the semantics. Usually the PCIe emphasis that's happening is it's actually a recent discussion, right? Believe it or not, it wasn't all that long ago before the concept of actually putting storage on a PCIe bus was a really radical concept, right? Nowadays, we're just like, oh yeah, sure, it's no problem, right? So we've already accepted and adopted things pretty quickly that we would not have normally have had before. We've removed an adapter that we don't necessarily need in order to do this inside of a server. That's why the questions are coming up as, wow, okay, so if I've got a memory space that I can access either using load store or I/O, why can't I do load store over a network? Maybe because it's a really bad idea. All right? But these are the kinds of questions that people are asking, and it's important to know where those limitations actually are. So the risk, however, is that we're trying to say, look, if I can get these things done with software, or if I can actually use the abstractions that this is going to provide me and capitalize that in software, can I then extend this without taking on a lot of risk? But if you don't know what the risks are, how do you know? Now, the remote storage, when I mean remote storage, what I'm talking about is remote from a server's perspective, right? Outside of a server. This is where we get into the religion discussions. This is where we start getting into the protocol huggers, right? The people that are really, really fond of Fibre Channel, really, really fond of Ethernet. I love to think, well, everything's going to be Ethernet, like as if Ethernet was a single entity for delivering storage, right? So the reality here is that each of these different things have reasons for why they are what they are. The fact that we have layer 2 versions of storage and layer 3 versions of storage and layer 4 and up versions of storage is important. It's significant. And with Fibre Channel in particular, we have a specific type of approach that we're taking as a philosophy for understanding the connectivity between these different devices. It's not just the I/O and it's not just the IOPS or the latency. It has to do with the philosophy of the relationships between devices. So when we start talking about block file and some object solutions inside of the data center, we have to understand where those trade-offs actually are. So, for instance, anybody remember the push for lossless iSCSI a few years ago? Okay. If anybody's read my blog on lossless iSCSI, if you do a Google search on lossless iSCSI, I think it's still probably the one that comes up. It is an inherently bad idea for anything above one switch. But all of the concepts and pushing for lossless iSCSI were single switch environments. But they said you don't need Fibre Channel because you can do the same thing with iSCSI just using a lossless environment. However, Fibre Channel has topologies. You have edge core, you have edge core edge, you have means and mechanisms for understanding how the back pressure on congestion actually work, which you don't have in a single switch environment, right? So just because of the fact that you can create an environment that looks and behaves at a small scale like something else does not mean that when you apply it in a normal environment, it's actually going to do what you think it does. However, those risks are not unavoidable. You have to pay attention to where those things are. You have to understand that not all storage networks are created equal. So you have to understand where the layer 2 gets applied. So that means you have to understand a little bit about networking. You have to understand where the Fibre Channel, if you want to do Fibre Channel because it's an end-to-end qualified system, you still have to know how to do proper oversubscription calculations. Understanding deterministic and non-deterministic networking requirements is critical, especially as we go into low latency storage devices. Again, we're buying time here with these new things. All right, what about long distance? You'll notice that we have pretty much the exact same thing. You can use object, FCIP, iSCSI, NFS, and SMB inside of a network, inside of a data center, right? So what's happening is that when we start talking about NVMe over fabrics, for example, what are we really talking about? When you look at these things, you have iSCSI, FCIP, object, and NFS, and SMB. Almost all of these things have something in common. That is, they're not block. iSCSI is block. But if I use iSCSI in a distance environment the way that I use it inside of a local data center, I get really bad things happen. When I have a host connecting over a WAN to a storage target, this is not considered a good thing. And yet I'm using the same protocol. So I'm using the idea of an NFS, SMB, FCIP, or object store for a different reason. Just because of the fact that I'm using the same protocol doesn't mean it's the same protocol. I know that sounded kind of weird, but think about it, it actually works. Okay? Global storage. Realistically, we're talking about objects at global storage levels. Right? And I'm not even talking about the cloud stuff because that you can do block and that kind of thing inside the cloud, but that's effectively using somebody else's data center. Right? So realistically, when we're talking about doing storage at a global level, we're really talking about object. And I actually heard a question yesterday about using NVMe over fabrics across the globe. Do not do this. You'd have the same problem as using iSCSI from a host to a target across the globe. Okay? Just not a good idea. Just because you can or you think you can doesn't mean that you should. Now the problem here is that the risks are the workloads and the capabilities are going to be mismatched. If you have a high transaction operation or high transaction workload, obviously an object store across the globe isn't going to work out in your best favor. So knowing these trade-offs at the global level is extremely important. Like I said, the propeller spins the other way. And then cloud storage is an entity unto itself because, as I said, it usually winds up being somebody else's data center, just like serverless workloads is using somebody else's server. You know, and realistically, when we start talking about how this actually applies, all the previous rules still apply. It just applies in somebody else's data center. Knowing what this is, saying that, oh, I'm just using AWS's block service, or I'm just using Google's file service, or whatever it winds up being, doesn't absolve you of the responsibility of knowing what the actual matching of your trade-offs are going to be. So, looking back at the big picture, you have to ask yourself what the sweet spots are for the technologies that you're using for. And again, I'm pleading for developers and architects to think in these terms, not just match up to what kind of protocol can do what you're looking for. You have to understand how does this affect the management. Again, I haven't been actually talking about the one major pillar of those storage forces, which is management, because it opens up an entire Pandora's box of hate and hope and hurt. Anything else that starts with H that you don't like. So, life cycles, what about how does this affect your purchasing and your procurement? Procurement. Try this again. Budgeting. How does it affect your budgeting? What about your upgrades? How do you have to deal with upgrades? So if you have to upgrade every single server by putting in a brand new driver, is that something that you're going to be able to do? Well, maybe you can do it if you've got 5 servers. Maybe you can do it if you've got a hyperconverged environment of 8 servers. But can you do it if you've got thousands of servers? And this is particularly interesting because when we start to talk about things like NVMe TCP, which is what's being pushed very heavily by Facebook, Facebook has a specific type of problem, right? They don't care about the performance of NVMe. They care about access for their applications. That's what the TCP allows them to do, not give them high performance using TCP. They don't care about that. So when you start looking at the upgrades, what do? They want to be able to upgrade their servers from a single location because they're running one application. They've got really intelligent software for their purposes to do phased rollouts of upgrades. All right? So to that end, they have a system on how to go about doing this. What about high availability and reliability? And we're going to get to this in a second, but one of the big questions is if I've got these different form factors and they all look exactly the same, I'm just putting them in different places of the rack, how does this affect the fact that my data may actually go bad? How does it affect my risk modeling, to an earlier conversation, about where the drives are going to fail and how I can actually mitigate that before it ever happens? All right, so let's do a little pop quiz here. You may have heard this question this week. What's the difference between using Fibre Channel versus RDMA-based Ethernet transports for NVMe over fabrics? Now, I'm not asking you to answer the question. I'm asking you how to figure out how to answer the question. And the reason I'm asking you to do this is because this question right here, as we'll see in a second, is not the real question. You have to understand from a development standpoint, from an architectural standpoint, from a vendor standpoint, and even as a customer, you have to know what are the real questions we're trying to answer. When people start talking about the differences between RDMA-based approaches and Fibre Channel for the use of NVMe over fabrics, for example, and this is just an example, we can come up with many, many more. What they're really talking about is the ability to do something called zero copy. What we're looking to do, and zero copy is actually really not zero copy, it's one copy. You still make one copy. And the reality of it is that you're trying to create data to be sent to a user application without having to hit the CPU at every single time. You want to try to bypass the kernel in order to do this. Now, RDMA, Remote Direct Memory Access, is a semantic which encourages that data handling and does it in a very efficient manner. But you don't actually need it in order to get efficiency. So realistically, Fibre Channel has had zero copy, or at least the functionality of zero copy, a long time before RDMA became a thing. All right. So in Fibre Channel, data is DMA'd directly from an HBA, bypassing the host CPU, to buffers passed into the user. Right? You actually bypass the kernel the same way that RDMA does. Different name, same functionality. So the difference between the way that we handle zero copy in Fibre Channel and RDMA are the APIs. So let me give you an example. NVMe over Fabric using RDMAs. The Fabric is using the RDMA protocol transactions, and look at that ladder diagram. You have the I/O read and you have the I/O write. You have the NVMe over Fabric's command, you have the write, and then you have the return. Now look at the ladder diagram for Fibre Channel. Do you see a difference? I mean, realistically, this is the same thing, it just has different command names. So, in that case, obviously looking at this horizontally isn't going to solve our problem. I can do the same functionality, the very reason why we're asking the question. I can do the exact same functionality with either technologies. I can do this, and it's not even a matter of who does it better or who does it faster. Because quite frankly, that depends on a lot of different factors, including load, distance, and so on. So when we start to think about these connectivity, it's not going to work the way we want it to. So what's going to help? Well, understanding whether or not we're talking about deterministic versus non-deterministic storage environments is going to help a big way. Do I want to have a network that is dedicated for the traffic, or do I want to use something that is actually far more general purpose? What about the transportability, or the transport locality? It's not just about the data and where it's placed, but also the transport itself. How about outside or inside management? Outside in, inside out. So if you have, like for example, there is a great blog article by a guy by the name of Eric Smith on Brass Tack's blog. I think it's a TypePad account. He's got a really fantastic article about outside in and inside out technologies for iSCSI and Fibre Channel, right? And basically Fibre Channel is a fabric-based architecture, which means that everything is located inside of a centralized name server. Whereas iSCSI is when you have to touch everything on every particular device. It's an outside-in management structure. Whenever you add iSCSI, you add it from the outside in. When you add Fibre Channel, you add it from the inside out. That's a management decision, right? And I've deliberately not talked about management in this particular talk because, like I said, it's a Pandora's box, and there are other places that is far more appropriate. But what's the bottom line? Effectively, we have to beware the law of the hammer. And this is true for developers, consumers, architects, basically anybody who is building something or wants to buy something. And quite frankly, if you can do this, you can arm yourself against people who are trying to sell something. Can you do the same thing with a different paradigm? What do you get? What do you lose? Are we just shoehorning the solutions just because we can? Remember, we were talking about the questions that are coming up with NVMe and trying to extend load store outside of the latency range into I/O realm. Just because of the fact that now we've changed the media from a regular NAND device into an NVMe NAND device, right? Different questions or different fundamental characteristics can lead us down a very appealing path until things go horribly, horribly wrong. So we have to be careful about this last bullet, and this last bullet is actually one of the most important. We have to be very careful about becoming obsessed with which technology is going to win. It isn't about which technology wins. It's about which technology is going to solve your problem. And quite frankly, the issue that you have to be aware of is if your problem is solved by a technology that doesn't win, are you going to be forced into doing something that you shouldn't do because you're afraid that the technology isn't going to win, whatever that means? People have been worried, I can't use tape because tape's going away. I'm going to tell you something, tape is not going away. All right? All seismic data is collected on tape. There are more exabytes of tape collected every year than the sum of all human knowledge. Every year, and it's all collected on tape. If everybody else goes away, and it's only the seismic industry, you know, the oil, gas, environmental, the weather, all these kinds of things, all using the seismic data from under the oceans, and it's all going to tape. So not using tape because of the fact that you think it's going away is a really silly thing because of the way that it's being used, right? So we have to be careful that we don't allow ourselves the luxury of eschewing technologies just because of the fact that you're afraid that it's going to win. So you have what I call the battle of the boxes, or more specifically, data on the stick. And I think this is a problem. Developers think about what's immediately in front of them. And that problem, and that issue, I'm just looking at the time, that issue is actually a big problem. Because what we do in SCSI is we throw things over the fence. In other words, think about the way that SCSI works and the relationship between a host and a target. I have a host, I have to talk to an adapter. I throw my processing command into an adapter. The adapter has to convert that into a SCSI language and then prepare it. That's an airlock. The CPU is like I've handed it off, and anybody who does the development on that, they don't care. Once it's over there, it's their problem. Now, what does the adapter do? The adapter takes the SCSI command and puts it into a specific transport protocol. Right? SCSI, it could be Fibre Channel, it could be InfiniBand, doesn't matter. But once you do that, once you place that into an adapter, I'm done. Another airlock. Now the network's got it. Network looks at this and says, hey, I've got a packet. I just have to shunt the packet over here. Hey, and once it's over there, I'm done. Another airlock. Now the SCSI packet's over on the target. Target's like, hey, look what I got. I got a packet. I process the packet, shunt it back over, I'm done. NVMe doesn't allow that to happen. NVMe does not work that way. The relationships between a host and a target are far more nuanced than just simply throwing things over the wall. So when we start to look at this problem, compute and server developers in particular think of this as a storage relationship. They will say to themselves, you know what, as long as I have access to the storage, I don't care. It's data on the end of a stick, I don't care. As long as I got access to it and it doesn't go away, I'm good. And unfortunately, that's where things are going to be very limited. Storage developers may not think of management issues. They think, hey, look, I'm doing my job, I'm protecting my data. But you have to go through all kinds of hoops to get to it, especially if something goes wrong. That's why hyperconvergence has been so fantastic of a market lately. That's why everybody's talking about hyperconvergence, hyperconvergence, hyperconvergence. It's not a storage problem. It's not even a compute problem. It's a management problem. And some of the tactics for going out and selling hyperconvergence in the industry, unfortunately I can say that I don't know of anything about this in my company, and I hope this is true, has been effectively to repaint the picture as a storage problem, right? They'll go up to people and they'll say, you know what? You know those guys behind the closed doors who tell you that you can't get volume for your virtual machine for 2 weeks? They've been lying to you. They don't, they're just basically, going out to lunch with these storage manufacturers. They don't really care about you. But you don't have to. All you need is what I've got to sell. I'll give you your storage volume right now. All you have to do is buy my hyperconvergence product, and you've got the storage right inside the box. You've got the management UI to do it yourself. Now, if something should go wrong, we don't know anything about that. If a drive fails or if a node goes down, I'm out, right? So knowing how these things work and how these things are actually being delivered is a key thing. And we'll talk a little bit about how NVMe works a little bit differently if I've got some time. But keep in mind, we already talked a little bit about the deterministic versus the non-deterministic. So let's find out what that actually means. Now, how many people are not storage networking people? Okay, we've got one hand. All right, so I'm going to go through this relatively quickly because quite frankly, you're already pretty familiar with this already. All right, you've got any-to-any connectivity, and you have your examples of really higher level layers to do this. The SMB stuff, anything that you can't preordain the relationship between a host and a target counts as a non-deterministic storage network. Unlike that, however, you have a deterministic storage, which means that the relationship between a host and its target are pre-known, are well-known. And so as a result, when we start talking about NVMe over fabrics, for example, and it sits on top of any different protocol, people can't look at NVMe over fabrics as a ubiquitous solution to a problem. It is a multifaceted approach to solving a particular storage problem. If I can do it deterministically and I can do it non-deterministically, that is not the right question to ask. Whether or not to use NVMe over fabrics is irrelevant if you don't know whether you're talking about deterministic approaches or non-deterministic approaches. Do you want to know in advance what's going to happen, or do you not want to know what's in advance what's going to happen? It makes a big difference. Now, this is a reference slide, but I want to show you how things can be kind of manipulated here. All right? So in this particular case, here I have taken all of the different approaches that we've been taking. I've been classifying everything, and my God, Ethernet looks really strong. Look at that. I've classified intra-host, direct attached, network attached, storage deck. I've got block storage, file storage, object storage. I can do global distance, and wow, Ethernet's just amazing. We got to use Ethernet. Well, wait a minute. What happens if we start broadening out things into a more vertical perspective? What happens if we start asking, instead of whether or not it ticks off the check boxes, that it actually follows through the philosophies of where our sweet spots are? These are connectivity options. This is a horizontal approach. This is a vertical approach. Now you'll notice that sometimes it's yes, sometimes it's no, sometimes it's maybe. And that's true for all different technologies. When you start to think about things from a vertical approach, you really have to be able to understand where in that schematic that we talked about, the mapping, you actually fit. So a real quick example, because we are out of time, or running out of time. Here's three different architectural examples. We've got hyperconverged, top of rack, and an array. All of these different methodologies provide block storage to host containers or virtual machines. They're all exactly the same functionally. But they're very, very different, not just in form factor, but also in approach. So, how do we make this determination? What is our data protection and our high availability? Which one does that the best? How are we dealing with scale versus management? Now, if we look at this, for example, our hyperconverged has great management, real lousy scale. If we're looking at the top of rack, it could be a nice blend of both, but you're still kind of limited in terms of the way that each rack is handled as a separate entity, and you have to treat it as such. Well, the array can certainly provide us with a great deal of scale, and it can provide us with a great deal of performance, but it's not quite as flexible in terms of our management structure. Okay, so you're going to have, your mileage is going to vary. What about performance consistency? All right, I'll tell you right now that architecturally speaking, hyperconvergence is not consistently performant. Top of rack might be, right? Especially when we start talking about really high high connectivity options. Some of the startups that are doing this are putting 100 gig links between the top of rack and the servers. Well, sure, if I'm going to give you an individual 100 gig link for your server, you're going to get pretty high performance, all right? But it also could be overkill, Most people who use Fibre Channel today using storage arrays that are out of flash only really push 4 gig. Maybe 5 or 6 total. They'll have 32 gig links, but they're not using them. All right? Those kinds of things are again, the trade-offs. I got it? Thank you. And then finally, you have to pay attention to what's going to happen over time. What about your growth, your updates, and your backup and procedures? So we want to avoid, at all costs, the technology's dead, long live other technology. Because how long have we heard these things? Tape is dead, long live disk. Disk is dead, long live SSDs. SSDs are dead, long live NVMe, right? And ultimately, you pick your poison, right? It's X is dead, Y, long live Y. And you also notice something interesting? It's always the other guy's favorite storage that's dead. You notice that? Just interesting. All right, so let's just take a quick look at this and summarize what we've been looking at. This is a plea. I'm begging people to think of things differently, at least in the approach of understanding what your adjacent knowledge sphere is. In other words, what's right next to what you don't know. You're very, very good at your core thing, but we have to forget about throwing things over the fence and expecting somebody else to have the problem. That it's not my problem won't work anymore. Okay? So understanding the reasons why you want to put together the storage solution, why you wanted to develop the storage solution. A lot of the startups that I have seen in the last 2 years, and so I'm an R&D engineer for Cisco, so I evaluate technologies. A lot of the startups that I have seen that never saw the light of day should never have been developed in the first place, because they focused on the horizontal and not the vertical. And that's why I'm trying to give you this little bit of caveat. Understanding the strengths and layers of each strength and weakness of each layer will help identify where those danger zones actually wind up being. Because if you don't know where the sweet spots are, you may actually miss them in their entirety. So there's a need for everybody, and I mean everybody, to be able to get out of their comfort zone and understand what their floor awareness really winds up being. And that's the end of my conversation. We do have 2 minutes, and I can take questions. If there's not, I can explain why NVMe is different from SCSI in this regard, but it's up to you. What do you think? Okay, this is the audience participation portion of the day.
So as things go, it feels like in the market there's going two directions. You mentioned hyperconverged. There's another model which is disaggregated. It kind of blows apart the compute storage paradigm, right? Where you're actually putting stuff. How does that fit into your vertical mapping? Will you move in the disaggregated direction? Does it follow it?
It does. It follows it right here.
Okay.
It follows it right here. So, yes, the question was, so we've heard a lot of talk about hyperconvergence and disaggregated storage, and in some cases there's some overlap, and there's some cases there's some differences. Where does it fit in terms of the vertical storage element, right? So the first place it starts is here. Why do you have hyperconvergence and disaggregated, often being sold by the same company, just using different form factors, right? So the real question is, what are the forces that they're trying to solve? If you have a hyperconvergence, why would you need to take it apart, right? Because the whole point of hyperconvergence is you're bringing things together.
Easier management, right?
There's the management side.
But disaggregates for scale.
Disaggregates for scale. So we found that by going into a particular form, we have limited ourselves in an approach. Right? So we have actually concluded too early that we need to go in a specific direction because it broke. We moved into the management side and it's broken the scalability. I've got lots and lots of storage that I'm not using. I don't have enough CPU power, but now it's the other way around. Right? So that goes back to the three different components that we were looking at in one of the last slides about hyperconvergence, top of rack, and array. Right? In that particular case, an array at the top, a top of rack appliance might be the most appropriate to help manage you can handle the storage separately from the actual compute by saying that we're just going to focus on the rack. But funny, isn't that what we used to do in the first place? But now what we're doing is we're creating an extra granularity to being able to do that, so that we don't have the array management that we have to do. Now you're just actually managing the direct attached storage volumes. And you can do that a little bit easier in smaller environments. Gotcha. So I've been given the hook, but I do want to at least get the opportunity for one more question if I can. Anything else? Bueller? Well, thank you very much for your time. I'm glad you were able to tolerate my rant for 45 minutes. Thank you so much.